to start today. So thanks again for attending, everyone. Today we're gonna kind of pick up where we left off yesterday. Yesterday we were kind of talking like the tectonic setting of this area. Why do we have lava and magma to begin with? So now we're going to be zooming more in on the Canary Islands. Obviously, our destination over the next week or so. So to kick us off, we'll do a quick little Geo 101 in volcanoes, so that we all have a good baseline understanding of what volcanoes are, how they erupt, what they form, and so. What a volcano is, by definition, is just a vent or an opening in the Earth's crust. And we all know what the Earth's crust is now. And so it's an opening in the crust that basically is a pathway for magma to rise up and move onto the Earth's surface. And so typically a volcano also has a mound or a hill or a mountain that is typically building around it and on top of it. Typically, the higher that volcano gets, that means the more active it has been throughout its history. In the word volcano, anybody watch Star Trek? I didn't watch Star Trek, but my wife did, so when I told her this, she told me that, and I was like, okay, I'll do that on the cruise. So the word volcano is derived from the Roman god Vulcan. And so Vulcan was the god of fire, and in their lore, they thought Vulcan lived within Mount Etna, where he forged his weapons with the magma that was in there. So that's why we call them volcanoes. Yeah, so volcanoes and us as humans. Generally speaking, we don't like when volcanoes erupt. They make our lives difficult. If you live near Iceland or even in the UK, when you have a big explosive eruption in Iceland, your air travel gets a bit wonky. Throughout human history, and really, you have to go more than a decade to see instances of explosive eruptions leading to fatalities. And so, humans have a long history of living with volcanoes. Some of them, are very iconic, especially on cruises. Pompeii. Probably one of the most popular tourist destinations in the world. And it's because humans have a very morbid curiosity. They like to see what happens when a town gets buried by a pyroclastic flow. And we'll talk more about those. And Pompeii was the result of Mount Vesuvius erupting in 79 AD. And that particular eruption, which is a painting by Pliny the Elder, or Pliny the Younger, I can't remember which one it was, it led to an ash layer that was 6 meters thick. And so leading to basically the permanent, casting of poor souls who were trapped in their sort of original positions at the time of that eruption. Okay, what's the difference between magma and lava? Which one? Yes, excellent. Magma underground, lava above ground. I always have to sort of start with that because that is, again, very annoying. Geology is a science of jargon, and this is one of the more annoying jargony things that we like to nitpick about. So, any what we call molten rock that is stored in the subsurface, whether it's in a magma chamber or in a conduit or in a vent, that's considered to be magma. Once it actually erupts onto the surface, at that point, it becomes lava. So it's just, where it's hanging out at that particular moment in time. Okay, so another important thing that I need to introduce, because it controls the way in which a volcano erupts, is its composition. So not all lava is the same, not all magma is the same. It varies quite a bit in its chemical composition. And the sort of mineral that we're most concerned with is silica, SiO2. It's a very common mineral. Does anybody know what mineral is made up of pure silica? So starts with a Q. Quartz, quartz. One of the most abundant minerals on the planet. And I will just throw a plug out there. They don't have magical powers as much as people try to sell you on them. I can confirm that it's just one silicon atom bonded to two oxygen atoms. There's no magic going on there. And so, yeah, the amount of silica that makes up that lava is going to have a really strong control on if you have an explosive style eruption or a more calmer, what we call effusive style. And I'll talk more about that. So if you have a low amount of silica, it's considered to be a felsic lava. That is the geology jargon word for that. If you have high silica, you have a mafic lava. And so when you see that lava solidify, felsic lava has a fairly light color to it, fairly light tone, while mafic lavas have a more darker tone to them. Anybody know what this rock is called? Yeah, basalt. You're going to see a lot of basalt on this trip if you get off the boat. Lots of basalt. And then felsic, this is probably a rhyolite. Can anybody think of a volcanic rock that has that color? You see it in Bed Bath & Beyond?
Pumice.
Yeah, pumice. So the main difference between pumice and rhyolite is, what makes pumice unique? Did I hear the word air? Yeah, it's got a lot of gas bubbles in it, so it actually floats on water. And I'll talk about that tomorrow. There's some pretty interesting eruptions that have in this area that have led to lava balloons that float through the water up into the surface. But yeah, so mafic and felsic, they lead to two very different types of eruptions. So felsic lava is very thick. It has a high viscosity. So viscosity is basically a fluid's resistance to flowing. So honey has a high viscosity, whereas low viscosity would be water. It can flow very easily. Felsic lavas also have a lot of dissolved volatiles in them. There's a lot of gas in that lava. Things like carbon dioxide, sulfur dioxide, water vapor. And so this is kind of analogous to getting a bottle of soda and shaking it up. And what happens as you shake up a bottle of soda? What does it do? It explodes. Yeah, you're building up the pressure from all the gas that's dissolved in the liquid in your soda. And so that's what's happening here is you have your volcano. There's some solidified rock on that vent that's basically trapping the magma within that volcano. And so as more magma gets injected, it's building up that pressure. That those gas bubbles are expanding, and eventually the pressure of that gas expansion will overwhelm the cap on the vent, and you get this type of eruption. Where, do you really see lava in here? We don't really see any of that like bright orange fluorescence material. And so what's happening is rather than having like a nice lava flow, you're having this violent fragmentation where this lava is being split into dust-sized particles from that sort of, think of taking the bottle cap off of a bottle of soda that you've shaken. That same sort of process is happening, just at exponentially larger scales. And so this is typically what you see from that felsic lava composition. And one of the things that can happen when you have a felsic lava is if your ejection plume, which we just saw on that previous slide, again, it's a mixture of superheated gas and ash. Sometimes that plume has a density that is greater than the surrounding atmosphere. So what happens in that case is that plume's not going to go up into the atmosphere. It's actually going to collapse and basically flow down the slope of the volcano. And we call that a pyroclastic flow. And pyroclastic flows are probably the deadliest feature of volcanoes. They're responsible for the most deaths from volcanoes explicitly over the last century. This was the pyroclastic flow when Mount Olsen erupted in Japan in 1991. I might be wrong on that. I think it was in the 90s. And eventually what happens is, it kind of looks like an avalanche. Instead of just being snow and air, it's superheated sulfur dioxide in volcanic ash at like 300 degrees Celsius. So a bit, avalanche is deadly, but this is, a bit more deadly. And what happens is, as it's flowing down the slope, it's entraining more air, and its density eventually gets to the point where it starts to dissipate up into the atmosphere and it ends. But yeah, this is an iconic example of a pyroclastic flow that I believe this one unfortunately killed about 30 people in the 2 minutes that it lasted. And so this is what buried the town of Pompeii, this type of event. Yeah, so if we don't have felsic lava and we have mafic lava, we have a more lower viscosity lava. It's more freely able to flow, and mafic lava has less gas and volatiles in it. And so it's less likely, to have all those bubbles begin to expand and violently fragment like we see with the explosive style eruptions. And so when you have that type of lava, you're more likely to see, maybe what we think of when we think of eruptions, where we have, molten rock that is flowing along the surface of the volcano. This is what happened when La Palma erupted in 2021. It was this style of eruption. When Iceland erupted a few months ago, it was this style of eruption. Okay, so depending on the type of eruption that's occurring, you're going to get two very different types of eruption products.
Excuse me.
Yeah.
Can you stop walking in front of the screen?
Oh, sorry about that. My fault. Is this good? Okay, I guess I'm standing in the spotlight now. So depending on the type of eruption that you have, you're going to have two very different types of eruption products. So if you have that really explosive felsic eruption, you're going to get a lot of volcanic ash, which is what we see in here. And then you might have some larger blocks, and we call these volcanic bombs. And these bombs are actually broken off of the volcano at the time of eruption. There's so much energy, there's so much shaking and vibration that chunks of the volcano itself actually break off and then get ejected with the ash plume. And so that's what we see right there. So you get these volcanic blocks, fragments of the volcanic structure itself, that then deposit with all of that ash that's going up into the atmosphere. That ash doesn't remain up there indefinitely, it eventually settles back down. When we have a mafic lava flow, you get something that looks like this. And this is, probably what you're gonna see, especially in Lanzarote, where it's essentially, it kind of looks like pavement of the earth. Those lava flows, once they get onto the surface, they start cooling, they start solidifying, and you get this strikingly black landscape that is forming from those cool lava flows. So you don't have like these individual sort of like sediment grains that are forming. It's more of like just like a solid sort of layer of basalt that's forming on the ground surface. And there's two different types of basaltic lava flows once they solidify. They're called pohoihoi and a'a. Anybody want to guess where those words were originated from? Hawaii. Yeah, Hawaii. Yeah, so pohoihoi is when the lava cools while it's moving at a pretty quick speed. And so you get this kind of like ropey ridge texture to the basalt. You can see it all through here. So if I were to go to lava flow and see that, that would tell me that, this lava was still moving pretty quick at the time that it cooled. The other style, the other texture is a'a. And so it's quite literally called a'a. Does anybody want to guess why? Say it again. Close. You say ah when you walk on it. And so it's a very like crumbly, brittle texture, pointy, and so they call it, they named it because that's what they would say when they walked on it. So it looks completely different from this. You could have a grand old time hiking on that, with your sandals on, but not so much with the flows. Okay, so how do we build a volcano? We're seeing volcanoes, we are seeing very large volcanoes. And so volcanoes are basically built, the larger that they are, that means that they have erupted many times over an extended period of time. Because for every time you have an eruption, whether it's a lava flow or a layer of ash, depending on the type of eruption, a layer of ash we also call tephra, is what's defined on the screen here. You basically, form one layer of that volcano. So when this volcano was young in this example right here, it formed that layer. It was just a little cinder cone. But as it kept erupting and depositing these additional layers, the volcano is essentially building itself up and out over time, to the point where you go from being a cinder cone to a stratovolcano. And I'll talk about the difference between those two. And so I want you to remember this, because when I talk about how we have volcanoes in the Atlantic Ocean, and there's really deep ocean here, it gives you a sense of how many times did this volcano have to erupt to actually build its way from the seabed to above sea level. Okay, so there's a few different types of volcanoes, primarily based on their size and their shape. So we have shield volcanoes. So shield volcanoes are the largest, like by an exponential amount, type of volcano that we have on the planet. And they kind of look like if you took Captain America's shield and laid it on the ground, it's just very broad and very gently sloping. And so these types of volcanoes are primarily formed from mafic lavas, where you have an eruption. Those lavas are so low viscosity, they're so easy to move, that they're able to flow over a great distance. And so an example of that would be Mauna Loa on Hawaii. So that right there, that is one very large volcano. And it's actually, trivia fact, it is the tallest mountain on Earth. Why is it the tallest mountain on Earth? Yeah, when measured from the seabed, it's taller than Mount Everest by a pretty significant amount. Maybe they'll put that in trivia later. That's one of my favorite geology trivia facts. So yeah, that's a shield volcano. All the islands, and I'll talk about this, all the islands that we're going to are all shield volcanoes. They are all shield volcanoes. Stratovolcanoes are, what you might think of when you think of a volcano. Like it's got that really distinct conical structure to it. It might have, a very explosive eruption. That's typically where you see explosive eruptions. You won't see them from shield volcanoes. You'll see them from stratovolcanoes, is where you see those big eruption plumes forming. And so Mount Fuji in Japan, very iconic stratovolcano. Mount Etna, stratovolcano. I'm trying to think. Mount Kilimanjaro in Africa is a stratovolcano. And so very steep-sided mountains, very conical in shape. And they can erupt both ways. They can either erupt explosively or effusively. They can have both mafic and felsic lavas. And then finally, the smallest of them all are the cinder cones. And so cinder cones are really small. You can hike up to the pretty symmetrical crater right there. You can hike up, probably within a matter of a few hours. They're really small. They're generally formed from less than 10 events. So they're very short-lived eruptions. And you often find cinder cones on much larger volcanoes. So Lanzarote. Lanzarote has a large volcano that we'll talk about. And then it's got a bunch of these smaller cinder cones on top of that volcano. So it's like a volcanoception. If you've ever seen Inception, a dream within a dream, a volcano within a volcano. Okay, so that is my quick 15-minute introduction to volcanoes. And so now we're going to be looking at volcanoes that we'll see on the cruise and different types of volcanic features that we're going to see that I think are pretty neat, but I might be biased. So port of call number 1, I had to change these today because you guys are a fine-tuned audience and you totally would have called me out if I said it was port of call number 2, but it's not, it's number 1, so I went through and changed all those numbers today. And I had to check my directions as well. And so we're going to Madeira tomorrow. And so Madeira Island, what we're looking at is basically the summit of a much, much, much larger shield volcano. So what I showed, Mauna Loa, the peak of Mauna Loa is what Madeira is. It's a massive volcano that's kind of just sticking out at the top above sea level. That's what all of these islands are. And again, on top of that, there's a bunch of other volcanoes. So at the end of the day, all of these islands, I won't mention this again, they're all shield volcanoes, but there's additional features on top of them because there's different modes of volcanic eruptions. So Madeira is fairly young. It started building about 7 million years ago, so that's putting it, roughly around the age of La Gomera. And it stopped erupting 700,000 years ago. And so 700,000 years ago is a long time. And what do we notice about the color of Madeira? It's green, which is vegetation. Yeah, exactly. So Madeira, it's called, what's the nickname for it? The Garden Isle. Yes, the Garden Isle. It's the Garden Isle because volcanic soils are very rich in nutrients. They are very fertile grounds for vegetation to grow. And if you haven't, there was, recent minor volcanism 6,500 years ago, so the island's actually considered to be dormant. The threshold between dormant and extinct is 10,000 years. If it's been more than 10,000 years, congrats, you're extinct. Or if it's been less than 10,000, you're dormant. So if it's been 700,000 years since this volcano has erupted, that's a lot of time for vegetation to grow. And the slide after this, I'll talk more about some other features because of that. This is what I was talking about previously about Madeira, where most of the island is underwater. And so Madeira rises about 6 kilometers above the seabed. So this is bathymetry data. And so I used to do this for work way back when. You go out and you basically mow the lawn and you measure the depth to the seabed. And so the colors from like the blues and the purples, those are negative depths, which means they're underwater. The brown colors are subaerial. They're above sea level. So there's Madeira right here. And you can just see how big the actual volcano relative to the island, how big the volcano actually is from a volume perspective. And so that volcano erupted so much, it started out at minus 4,500 meters and built up through over 4.5 kilometers of water, slowly building its way up until eventually it broke sea level at 0 meters, that's sea level, and now it's built up to about 1,650, 1,700 meters at its maximum elevation. So that's a lot of eruptions. That's a lot of material that this particular shield volcano had to erupt in order to build above sea level. So that's a testament to how much magma, that mantle plume that we talked about yesterday, how much magma is being generated by that mantle plume. So the last thing about Madeira that is, I wouldn't say it's unique to the island, but it's one of the really cool things to see, is what they call ribeiras, otherwise known as a deep ravine. And so when I mentioned that this volcano hasn't erupted for 700,000 years, well, if that's the case, what takes over is erosion. And so anybody want to guess what the main agent of erosion is on this island? Erosion is the process of removing rock and material. Water, yeah, exactly. So these ribeiras are these really, really deep valleys that have been carved into the island after 700,000 years of pretty substantial rainfall. It's a fairly wet climate in Madeira. And so, yes, you're getting all that vegetation. You can see it looks like Hawaii. It's incredibly fertile, and that's from the volcanic material that's present. But then you also get these like striking canyons and valleys that have formed. And that valley that we see right here, that used to have volcanic material in it. But it has all since been eroded from water that is flowing through this region into the offshore environment. And so if you're driving around the island, you're probably going to see, some really steep cliffs, because I'm sure that's where they build their roads, is through these naturally formed valleys, because it's an easy place to drive through. And so if you're hopping around the island and you see these large valleys in these, what we call a scarp, those are ribeiras, and they're formed from erosion due to how long it's been since this volcano last erupted. Okay, so port of call number 2 is San Sebastian de La Gomera. And so La Gomera, like I mentioned, is also the summit of a shield volcano. It's kind of analogous to, I think an easier way to analogize it is like an iceberg. I know my office had this poster, one of the classic motivational posters where like it shows an iceberg and like the upper 10% of it you can see above sea level, and like the lower 90% is underwater because that's isostasy and buoyancy. Kind of the same thing with these shield volcanoes. Really the only upper tip of them is above sea level. And so what do we notice about La Gomera? Circular. What? And I heard green. Yeah, so definitely it is also very fertile. It's heavily vegetated. The tour that I wanted to escort sold out, and I was very disappointed. So if you're going on the Las Rayas hike through the national park in the center of the island, I'm very jealous, and I would like to see photos. And so the reason that this island is also vegetated is because it hasn't erupted for 2 million years. So it is very much an extinct volcano. We do not have to worry about an eruption when we're there in a couple of days. And yeah, you can also see just from this satellite photo, these are all valleys that have been carved into the volcano, emanating all throughout like the central island part. And so this island is being extensively dissected by rainfall. Yeah, so one of the coolest geological features on the island is Los Organos Natural Monument. And so Los Organos Natural Monument is a great example of columnar basalt. Has anyone ever been to Giant's Causeway? Yeah, so it's the same thing. Really, really interesting, just sort of natural process of lava cooling is what's happening here. So when you have a magma chamber, that is cooling over a slow period of time. Whenever you cool something, whenever you cool any solid, it shrinks because of the ideal gas law. And so if your basalt or whatever your volcanic rock is cooling and contracting because it's become essentially a dead volcano, it eventually sort of just shrinks and forms these polygonal columns that are, stacked one right next to the other. And so this is a really, really great example, a really, striking setting to have one directly on the coastline. So if you can get to it is located, so as I understand it, we are docking here, I believe that's San Sebastian. Which, by the way, I'm a Yank, I have to say this. It was the last stop that Christopher Columbus made on his way to America. I learned that today. That was pretty interesting. So we're stopping there. And then I believe that monument is up on the north side of the island. And so, bit of a drive, I would gather. I can't imagine it's too easy getting across this landscape. But I just wanted to share that because, if you've been to Giant's Causeway, then you've got a pretty good experience of what these look like. But if you've never seen them, they're a really, really cool geological feature to see in person. And it's all a product of that basaltic lava cooling slowly over an extended period of time, and it's shrinking into these polygonal columns. Yeah, and I know one of the tours goes here. Roque de Agando. So Roque de Agando is one of the 5, I think there's 5 of them, known as Los Roques. And so these are volcanic plugs. So a volcanic plug is essentially when you have a magma chamber that has cooled and solidified. And so a magma chamber that doesn't completely empty. So you imagine you have a volcano, there's some magma sitting in there. It doesn't actually erupt, it just solidifies. And that's it, that's the end. And so that rock that has solidified is gonna be, fairly strong, fairly resistant to eroding. And all the material around it, the volcanic vent that has since been removed, any soil has been removed. So that's what a volcanic plug is. is you can basically imagine that there was a volcano right here, going like that, above the screen, going through floor 9 or floor 8. All that material has since been removed, and now on the surface, that magma chamber that has since solidified is now exposed. And so that's what the Los Roques are. And I know one of the trips is going there. And they have actually found some, I don't know if one of the other speakers talked about this, but they actually found remains of sacrificial shrines on these Roques. And so I believe they're like a protected area now. And they were found at the summit. So can you imagine climbing a near vertical face without any, I'm assuming they didn't have ropes and lines back then. And that was the Guanche people. And so they were the native inhabitants of the Canary Islands. Okay, port of call number 3, Santa Cruz de Tenerife. So Tenerife has some accolades. It's got some trophies in its trophy room. It is the tallest of all of the Canary Islands at 3715 meters. And it's also the highest point in Spain and the highest point in the Atlantic Ocean. And so, that's some pretty cool things to brag about. And when measured from the ocean floor, it is the 3rd tallest mountain in the world. And that is going to be behind Mauna Kea and Mauna Loa on the Big Island of Hawaii. So a pretty massive volcanic feature. This volcano started at the seabed and erupted its way 7,500 meters in height. That is just a massive amount of volume of material. And so that is the summit of the shield volcano right here of Tenerife. Now, the volcano that everybody goes to on Tenerife that has the national park associated with it is Mount Teide, which is right there. So Mount Teide is a stratovolcano that is built on top of the shield volcano. So it's a volcano on top of a volcano on top of a volcano. And so when you go to the summit of Mount Teide, that is where the 3715 meter elevation is. And so this is just a great shot here. I think this is from the International Space Station, where you can see Mount Teide and how it's situated within the caldera. So you see that circle right there? That's the caldera of the entire shield volcano. And it's the Mount Teide is completely within that caldera. And I'll talk more about that. Yeah, so Mount Teide, sorry, I got a little ahead of myself there. So you can see here, it's that classic stratovolcano structure, that really steep-sided, fairly conical structure to it. And it started forming about 170,000 years ago. So relative to the age of Tenerife, which, if my memory serves me correct, was about 11 to 12 million years old from the talk yesterday, 170,000 years ago is really not a long time ago in the grand scheme of the island. It's fairly young relative to the island as a whole. And it last erupted in 1909. And I'd be curious to learn of the recurrence interval, which is how frequently volcanoes erupt. See if we get some insight on when it last erupted. And what do we see? You can see that black landscape right there. Those are all basaltic lava flows, mafic, that are just flowing down the slope of the volcano. You're well above the clouds here because, again, we're at 3,700 meters elevation. That's really high. You probably need some degree of elevation. What do they call that? When you get to really high elevation, they stop you at some point because, acclimated. You have to get acclimated at some point, probably to get to the peak of Mount Teide. I don't think it's possible to get to the peak on a cruise tour. I don't think that would be fun. Your lungs would not have a good time. And so Mount Teide is one of what we call the decade volcanoes, one of 16 decade volcanoes, which was determined by the International Association of Volcanologists and something else that I can't remember. It's a long acronym. And it's basically the 16 volcanoes that have a history of large destructive eruptions very close to population centers. So Mount Etna is one of them, Vesuvius is one of them, Mauna Loa is one of them. And so they have a lot of monitoring that goes on Mount Teide. And again, the tour sold out. So if you're on that 4x4 Jeep tour to Mount Teide, take pictures, please. Yeah, and going back to that caldera that I was talking about. So there's craters and there's calderas. Both of them are that summit depression that we see in a volcano. You know, we saw it on SB Crater in Arizona on that slide. Mount Teide right here, that's its crater. So why craters form is when you have an eruption, the magma chamber empties. What's left behind when the magma chamber empties? What is it basically? Space. Yeah, it's air. It's like a cave. And so if you have a cave and then you have a bunch of rock on top of that cave, that rock is gonna collapse down into the magma chamber that has since been emptied. And so that's what a crater is. And you can see that there on Mount Teide. That is the crater for the Tenerife shield volcano. So compare the magma chamber size of the shield volcano of Tenerife compared to the magma chamber of Mount Teide. And the distance from one end of the caldera, the Las Cañadas caldera, from one end to the other is 15 kilometers. And so it's if this shield volcano were to erupt, it actually wouldn't erupt explosively because it's mafic in composition, but Yellowstone's caldera is over 50 kilometers wide, and it erupts explosively. So to put that into scale with a pretty significant volcano in its own right, Mount Teide, we really don't want Yellowstone to erupt. And so the threshold from going from a crater to a caldera is 1 kilometer. Once that distance from one end to the other gets above a kilometer, that's when it's termed a caldera instead of a crater. But they're both the same thing from a mechanistic standpoint. It's just collapsing down into a magma chamber that's been emptied. Okay, and then not the last stop, but the last stop of volcanoes is Arrecife in Lanzarote. And what do we notice about Lanzarote from space? It's brown, yeah. Not a whole lot of vegetation. Looks pretty parched on Lanzarote. Lanzarote is the oldest shield volcano on the Hawaiian Islands. The Canary Islands. It was the first to form. It was the second to form behind the Fuerteventura. It's about 20 million years old, but it has very recent volcanism, like within the last few hundred years. And so because of that, any vegetation that was present on the island, just gets obliterated when there's a lava flow, whether it's from a mafic lava flow or ash. Both of those different types are going to devastate any vegetation that was present. And so Lanzarote has a very sort of, lunar moon-like appearance to it. When you look at the moon, those like black splotches on the moon? When you look up at it, if you go up tonight, hopefully we can do it. If you look at the moon in a telescope, you see these like black seas. We call those lunar maria. It's all basalt, which is why it's black. And so it kind of looks similar to what we see right here on Lanzarote. And so the big destination, and I'm getting to this one. It was not sold out, so I'm pretty stoked, is Tamanfaya National Park, otherwise known as the Fire Mountains. And so the Fire Mountains are what we call a volcanic field. Rather than eruptions happening from a single vent, there were eruptions that were sort of popping up all over the place. And what do we call these? Yeah, cinder cones, exactly. So little pimples on the surface of the much, much, much larger shield volcano. And so these formed primarily in 1730 to 1736, so 6 years of active eruptions, with a secondary period in 1824. So only 200 years ago. And so you're starting to see some vegetation that's taken hold, starting to grow. But again, it's going to be very desert-like, very lunar-like. And these particular eruptions that happen throughout all these cinder cones It created 1/4 of the entire landmass of Lanzarote. So that area right here, that was all formed over the last, well, it formed 300 years ago within a matter of 6 years. Which is why it's so strikingly black, is because it's fairly young volcanic deposits. Yeah, and I think one of the coolest trips on this cruise is the trip to Jamellos de Aguas. And Jamellos de Aguas, is anyone going to Jamellos de Aguas?
Yeah.
Sweet. Yeah, so Jamellos de Aguas is a lava tube. Well, it's not a lava tube. Jamellos de Aguas is a theater, it's a restaurant, it's a lagoon, but it's all built into lava tubes. And so Lanzarote has one of the longest lava tube networks out of any volcano on the planet. Lava tubes are actually kind of like the last frontier. We've mapped by man maybe 5% of them because they're very dangerous to go into. And what a lava tube basically is it's formed from mafic lava flows. So you got your incandescent lava flow, it's speeding along, it's moving pretty quick. What starts to happen is the outermost layer of that lava flow is exposed to the air, and the air is cold. And so the upper part of that lava flow begins to solidify and cool. And it forms this kind of shell on top of that lava flow. And that acts as an insulating layer. It allows that lava that was, deeper down at deeper depths to continue to flow and not solidify, which is exactly what we see right there. Now, two things. This represents a very significant risk to humans, and this has happened on the Big Island of Hawaii. It's called Shelly Pohoihoi, because it's like a shell. It's like an outer shell, like an eggshell. And what's happened in the past, in I believe like the 50s and the 60s, was tourists would go out hiking in what they thought was a lava field, but they would punch through that shell and actually fall into the lava flow. Fortunately, this one here is pretty thick. That's a really well-developed one, using this very eager geologist for scale. And so what eventually happens is, the volcano eventually stops erupting, and this lava flow, what's left behind is a tube of where that lava once flowed through. And now at Jamellos de Aguas, it makes for a pretty damn cool amphitheater. Or, yeah, I think it is an amphitheater. There's, stadium seating from where this photo was taken. So if you go into Jamellos de Aguas, that's what you're going through. You're going through one of these lava tubes that has since stopped flowing, fortunately. Okay, so that is it for today. Hopefully that piqued your interest for what we're going to see over the next few trips. Tomorrow, I'm going to be talking about what is going on under the water, because hopefully one of the main points from this talk was, most of these volcanoes are under the sea. Cue aerial music. And so tomorrow we talk about what's going on beneath the waves, and then also talking about a very interesting eruption that happened in 2011, where we saw lava balloons, which is pretty interesting. So with that, I'll see you tomorrow.